All right, I think everything is now finally connected up appropriately, so we should be good to go. Um, yeah, so exam on Wednesday and covers chapters 5, 7, 10, and 12. All right, so let's pick up kind of where we left off last time. We were starting in on looking at doing more complicated extraction problems, liquid extraction problems, and I think we left off in, get to the right spot here. We left off starting to talk about dilute type liquid extraction systems, and in fact we were going to restrict ourselves, at least initially here, to very dilute systems. So under those conditions, then, we had that the raffinate and the extract streams would be constants. We're also making the assumption in these problems right now that the diluent and the solvent are immiscible. Okay. All right, so we derived essentially an operating line last time, and we commented that we could start to think about using McCabe-Thiele to be able to determine a number of equilibrium stages for some of these separation problems. Why don't we go ahead and actually try this on a problem then? And so we'll take a look at this example, and then I'm going to have some comments beyond, I think, this example about the separation that's occurring in this problem. So here's the situation. We have a feed that contains a 1 weight % mixture of acetic acid and water, and we're going to extract that with 1-butanol at a pressure of 1 atmosphere and a temperature of 26.7 degrees C. In the situation that we're given, we have available a solvent stream at 44 kilograms per minute of pure butanol. And we also have a second solvent stream that's available that's 30 kilograms per minute of 1-butanol, but it contains 0.4 weight % acetic acid. So it's got some acetic acid in it. And we're told here to devise a scheme to carry out the separation. We need to find the outlet flow rate and concentration of the exiting butanol phase, find a number of equilibrium contacts required to do the separation. So we're not starting off with the simplest problem here, because we're actually given a case here where we're going to think about putting in 2 solvent feeds, but one of the feeds already contains some of the solute in it. So if we were starting just from scratch on this, we would start to think about how might we achieve this overall separation. I mean, one scheme would be to say, okay, I'm just going to use the pure solvent that I have. That stream is only 44 kilograms per minute. So that would be an option. We could run this scenario and see what kind of separation we could achieve. Another scenario would be to think about maybe taking the 2 solvent streams that we have and mixing them together. All right, that's going to dilute the acetic acid down further, but it's going to limit the lowest amount of acetic acid that we might be able to achieve with this system, right? Because that stream already has a certain amount in it coming in. Or we can realize what's actually going on in the separation equipment, right? We know that the concentrations are changing continuously as we go through at each equilibrium stage. We're coming in with a feed that has some significant amount of acetic acid in the water. It may be that it's possible for us to think about feeding the solvent streams in at two separate locations within our equipment. And in fact, that's what we're going to actually do our analysis on. And we've already kind of jumped ahead to at least this diagram, which shows what we're thinking about doing. So we're coming in up here with a water acetic acid stream. We're running it through our separation equipment, coming out with a much reduced amount of acetic acid in the water. We're going to feed in the pure solvent at the location where we're coming out with the minimum amount of acetic acid in the water. And then as we go through our separation equipment, we're going to try to feed in our second solvent stream at a location approximately where the concentration would match up with that. In fact, we're going to force it to ultimately, as you're going to see, but we'd like to feed it in at a point where it would kind of make sense to do that as well. All right, and then we're going to come out the top with an extract. So that makes sense for everybody, what we're thinking about doing? We have to go through the details of figuring this out, but I think conceptually we need to understand that part of it at least, where we're headed for with it. Okay. All right. So for these liquid-liquid extraction problems, we have our terminology that we use. Our solute in this case is acetic acid. We'll label it A. Our diluent is water. We can label it W or D for the diluent. Solvent is 1-butanol. Label it as S. We got a raffinate stream, so that's any of the water streams. And the extract streams are any of the butanol streams that we're going through the system on. Okay. So we've settled on some sort of a scheme over here where we're feeding the solvent in at two different locations. What are we trying to find? We're trying to find the number of equilibrium contacts, right? So if I was thinking about the unknowns, certainly it would be N, right? And we want to find outlet flow rates and concentration of the exiting 1-butanol phase. Okay, so the 1-butanol phase that's exiting would be the extract stream that's exiting, right? So what does that mean? What's our other unknown? Y1, right? Y1 is where the extract exits, correct? Okay. Very similar to the way we've been setting up a lot of these other kind of separation problems, right? In terms of the inlets and outlets to our equipment. Okay. For this problem, given that we're kind of we're setting this up as this dilute system where we can apply McCabe-Thiele to it, we're also probably assuming that these two streams are immiscible. Okay, so, and we will examine that assumption here coming up. We'll assume immiscibility. So that basically flow rates are constant. Okay, so that's the setup for this problem. Where do we head for from here to solve this problem? McCabe-Thiele requires us to have what? Equilibrium information, and we also need what? Operating line. This problem, given the fact that we're feeding some solvent with some acetic acid in partway through our system, means what about the flows? There's going to be a different flow in different parts of our equipment, right? In fact, this lower portion down here, before we feed in this extra solvent, has one set of flows, and up here we have a different set of flows. So this is kind of like thinking back to distillation type problems, right? Where we had different flows in different parts of the column, above and below the feed. This is a case here where we're going to need more than one operating line. So we're going to need an operating line for this lower section and an operating line for the upper section in order to solve this. So we'll combine that with our equilibrium information and then think about determining number of stages. All right, so that's what we're headed for. So let's go work on this. So that means we need operating lines for both above and below where the solvent feed comes in. And for our purposes, we'll go ahead and we'll label anything that's above where the solvent comes in, just as our usual symbols, R and E for raffinate and extract. Below, we'll use a bar over top, just kind of like what we did with distillation. Okay. So we need top and bottom operating lines for the system. Why don't, I mean, that's certainly where we're going to head for here. But even before we get there, we need to know something about the equilibrium setup for this. And so in your textbook, there's a table. Table 13.3, which lists some distribution coefficients, constants for some various systems. And this particular system happens to be in there. And so this table basically suggests to us that y is equal to 1.613x. And what are these symbols? All right, so y is equal to the weight fraction of the solute, which is our acetic acid, in the solvent phase, which would be in what? What's the solvent phase for this problem? Butanol. All right, so 1-butanol. And so x then is equal to the weight fraction acetic acid in the water. Okay. All right, so we'll use that for this problem. We'll come back and revisit this in a moment. In terms of setting up this equipment, we're going to have multiple stages. We could think maybe, we looked last time at some of the different types and forms of these liquid-liquid extractors. For this system, say we have a vertical system and say that we have various mixing stages throughout this system. We still have to have the water and the butanol moving kind of in opposite directions a bit with us as well, right? I mean, we know that, right? Where would you want to feed the more dense material? The top or the bottom? Top, right? Because you want it to fall down through the system, right? And you want to feed the less dense material at the bottom so it rises up through, right? So that means that we also need to think about the densities of basically a water and a butanol. All right, so let's go, if you go and you find some density information, and I'm not going to be particular about this, say roughly at room temperature, just to give us an idea. The density of our butanol, essentially 0.81 grams per cubic centimeter, and the density of our water is approximately equal to 1 gram per cubic centimeter. So that suggests to us that we should do what? We should feed the water at the top. So feed water at the top of the column. And we already know that we're going to feed the 1-butanol stream in the middle of the column because it contains some acetic acid. And it's significant enough that if we were to feed it then at the bottom of the column, we wouldn't be able to reach the level of acetic acid concentration that we want in the water in that exiting stream. Okay, so let's proceed with operating lines. So we need operating lines. That's top and bottom. So let's look at the bottom one first. The bottom one. We already know the general form for our operating line. We worked on that last time. And so we would have something that would look like this. We would say that y is equal to r bar, because we're dealing with the bottom of our system, divided by e bar times x plus yn plus 1 minus r bar over e bar times x sub n. Where, what do we know about these terms? We need r bar and e bar. So what are those values? Let's flip back a slide and take a look there. What is r bar in this problem? R bar is associated with the water stream, right? Same as R in this case, right? We're assuming immiscibility throughout the system, and so this would be, we'd also have down here R is equal to 100, right? As well. Okay. E bar in this case is what? .44. Yeah, it's before we get the second stream coming in. So we've got, in this case then, we've got 100 over 44, which is equal to something like 2.273. So now we know the slope of this operating line. Do we know a point that this operating line passes through? Oops. Do we know a point where this passes through? What's the point?
You can use
The
the formula and just find the b.
formula and find what?
Find the b, the intercept term.
Yes and no, but in order to do that, I still have to know a point. Right, I still have to know a point that that operating line passes through. Do we know enough information right now to figure out a point that it passes through? That bottom operating line, does it pass through any points that we know?
Passes through x sub n, y sub n plus 1, right?
It does. It does. And so we know both of those values right now, right? So, so I'll say this passes through x sub n yn plus 1, which in this case is equal to 0.001, comma 0. Okay, so we've completely defined the bottom operating line at this point. Let's go consider the top operating line then. Okay, this is for the top. We already know what the line should look like. It's y is equal to r over e times x plus y1 minus r over e times x naught. All right. Do we know the values for r and e? We know that r is equal to 100. What's e equal to? 74, right? So it's equal to both feeds coming in. E1 plus E2, 44 plus 30 equals 74. And so that gives us an R over E equals 100 over 74, which gives us something like 1.351 for our slope. So now we know the slope. We need a point at which this passes through as well, right? In order to figure it out completely. What point is this going to pass through? And do we know enough information to identify it completely? So let's go back a couple. So what point does this go through?
X naught y1.
It's not in y1. Do we know y1 right now? No. Is it possible to find y1? Mass balance. Let's consider doing that then. Okay. So let's just say one point on this line is x naught y1. So we need y1. So we're going to think about a mass balance. What mass balance should we do? Since we want a weight fraction of acetic acid, we should probably do a mass balance on acetic acid, right, for the whole column. So why don't we go ahead and do that? Let's just take a quick look at our diagram again, and we'll write down our mass balance. So in terms of the acetic acid mass balance, right, we have overall, in terms of just number of streams, we have we have 3 streams coming in and 2 streams exiting in the system, and we've got to count for acetic acid in all those streams. So let's do that. So we have essentially coming in R times X naught. We have E1 times yn plus 1. We have E2 times y s2, we'll call it. That's that side stream coming in. And then that has to equal what's leaving, which would be R times X sub n plus E times y1. So that means now we can solve this for y1. y1 is equal to R x naught plus E1 yn plus 1 plus E2 y s2 minus R x sub n divided by E. And we know all these values, right? So we're going to have 100 for R. It's constant all the way through. That X naught, that's what's coming in. That was 1.2 weight percent, so 0.012. E1, that's what's coming in as 44, but it's pure solvent, so yn plus 1 is 0. Plus, then the side stream is 30, and it has a concentration of 0.004. and then we're going to subtract off r, which is 100 again, times x sub n, and that's what's coming out. We wanted 0.001. We'll divide that by e, which is the sum of e1 and e2, 74. And so we get from this y1 is equal to 0.0164, let's say 86. So that means then that our point x naught y1 is equal to, in this case, our x naught value is 0.012, and our y1 value is 0.01649, let's say. All right, so that gives us a slope and a point, so now we should be able to construct the top operating line as well. Let me ask you a question. Would there be another way of locating a point for this top operating line based upon the information that we're given in this problem?
Can you plug in the side feed into bottom operating line, and that's where top would intersect it?
It is. That's exactly it. Because we know, we essentially have a feed line, and we know what it is, because this y is a constant right there. And we know that everything should intersect at that point, putting it in at the optimum place for us. So why don't we, let's go ahead and do that as well, just to see this. We'll call this a second point, is the intersection of the bottom operating line and side feed line. And so in that case then we would have our bottom operating line was y is equal to r bar over e bar times x plus y n plus 1 minus r bar over e bar times x sub n. And of course, for our side feed, we know that ys2 is equal to 0.004. Right, so we substitute that in. We can solve this for x. So x is equal to, I have to multiply through by e bar over r bar, so this becomes e bar over r bar times y minus yn plus 1, and that's going to cancel over here with these two. I bring it to the other side, I get plus x sub n. And so we can go ahead and evaluate this. This would give us 44 over 100 times 0.004 minus 0 plus x sub n, which is our 0.001. And so that would say that this x value is equal to 0.00276. So the point 0.00276 comma 0.004 is also a point on that top operating line, because that would represent the intersection point where they'd have to hit. All right, so we have more than one way of doing this. All right, so what's left to do? Well, actually construct the McCabe-Thiele plot. All right, so we know how to do that, so I'm going to actually just give you what it should look like. We plot first the equilibrium line, which we had. We knew it. It's a straight line. And then we start plotting the operating lines. We plot a bottom operating line, given the information that we had. We plot the top operating line either using this point here, right, where the feed, side feed, intersects with the bottom operating line, the known slope, or we use this point up here, which we calculated with a known slope. Put both of those in. Again, just reiterate, I mean, our two operating lines are crossing each other right on our feed line, the optimum feed location. And then what remains is to essentially step off stages for this. And so we step off stages, work our way down through. It gets kind of tight here on this plot, but we can get through it. And so as a result, then we know the ultimately the number of stages that we end up having here, which looks like how many? How many stages do we need? 15.4 stages, yeah, is what it looks like for us. And so at this point then we've addressed essentially all the questions that the problem asks. But that's how we go about doing a problem like this. Very similar to what we've done before, just now that we're doing it with liquid-liquid extraction. Questions about this? Anybody has? All right. I want to come back to thinking about this problem, but I'm going to do that after a couple of slides. So just bear with me for a couple of slides, and we'll come back to this for a moment. Dilute multi-component liquid-liquid extraction. How do we approach those? Well, we do it exactly the same way as we considered stripping and absorption type problems. If it's dilute, then each solute is independent. Typically, that means that for at least one of the solutes, we know enough information about how much of it we want removed, let's say, from our diluent, so that we can completely then specify the system. In other words, with at least one of the solutes, we can figure out the number of stages that we need. And then if we know the number of stages, then you can go back and evaluate, say, concentrations for your other solutes. Okay, exactly the same methodology as we did before. Okay, make sense? Yeah. All right, so nothing different there. So exactly the same. When we have dilute systems, we have essentially an equilibrium relationship that's linear. It means we have a straight line there. It's an opportunity for us then to apply a Kremser methodology for this, just as we did previously for absorbers and strippers. Usually our equilibrium relationship is such that given a linear system, usually the intercept is 0 for that equilibrium relationship. So that means that we have a pretty simple relationship between y and x, and that means that the slope is given by that partition coefficient, essentially, that we have, right, or distribution coefficient, whichever one you want to call it. So with that, then we can go ahead and use the Kremser solution, because same thing applies. We've got straight operating lines, we've got straight equilibrium lines. Kremser equation then allows us to evaluate, for instance, the number of equilibrium stages required. As you recall before, when we dealt with absorption and stripping, this would have been in terms of L and V. Now it's going to be in terms of R and E for us. So again, you can use Kremser equations for these kinds of problems. There's a special case here. The special case that we're considering first is that R over ME is equal to 1. When that's true, what does that say about the operating line slope and the equilibrium line slope? The parallel, so they have to be the same, right? Because that's the only way that you can have that to be true. Okay? But generally speaking, it's not true. And so this is our, as we did with absorption and stripping, right? There were a variety of Kremser equations. We can do the same thing here, except again, now we're going to use R and E. We're going to call this combination of terms here, we'll say M times E over R, where that's the same thing as our distribution coefficient times E over R. That's called the extraction factor for us. Okay, we're going to call that the extraction factor. And so when that term is greater than 1, that means that there's more solute in the extract coming out, which is what you want. So generally speaking, that's going to be greater than 1. You want that value to be a little bit bigger than 1 to make this practical for situations. I don't know, practical minimum, depends on your system. Might be around, it's going to be certainly a little above 1, might be as large as 1.3. 1.3 might be pushing it a bit, but certainly something a little bit over 1 will allow us to get there. What happens if we consider concentrated immiscible extraction? Immiscible means, again, we still don't have any exchange of the diluent into the solvent stream or anything like that. But we have a concentrated solvent, which means that solute, excuse me, in this case, which means that our flow rates aren't going to be constant in our equipment. So we're going to do the same thing that we did before. We're going to define ratios now instead of mole fractions or weight fractions. And so our ratio will be, say, kilograms of solute to kilograms of diluent and kilograms of solute to kilograms of solvent. And so that'll give us our capital X, capital Y. With that, just as we did before with absorption and stripping, we can construct operating lines based upon using capital X and capital Y. We can also calculate our equilibrium data as well for those systems and go ahead and do the analysis just as we've done in the past. All right, so nothing new there with that kind of setup. Okay. All right. We're going to do a problem using this. I don't think we're going to do it today. We'll probably wait till Monday, and that'll kind of wrap us up for this chapter. There's a lot of other aspects to this chapter, which I don't know that we have time to cover, because I would like to at least get us an introduction into chapter 14 as well. But we'll see. We'll see what we can get to. So that's the last slide for this chapter 13b. I put out some additional slides that we'll be using, but rather than jump to them right now, I want to at least first take a look at the system that we were just examining, right? So we were treating an acetic acid water butanol system, right? And we made the assumption in our problem that they were immiscible. Turns out they're not immiscible. In fact, there's a significant amount of miscibility. This is a plot that I found. I went and I did some looking. First off, the value that we used for our distribution coefficient shows up in a table in our textbook. That ultimately came from something known as Perry's Handbook, which is Perry's Handbook for Chemical Engineering. And they list a lot of different combinations in there. So, and there's a reference to a paper where they got some of that. But I went and I looked for some other information about it. And I was kind of curious because I really thought that the butanol and the water were going to have some miscibility. And it's certainly true that they do. In fact, significant amount actually. And so this is what the actual phase diagram looks like. This is somebody actually collected some data on this. They, in the same paper, go through and provide enough information here that you could attempt to get a distribution coefficient from this. So with this plot, they've got weight percent acetic acid in the solvent phase, and one of the solvents here is our N-butanol. And so that's these triangles, green triangles here. And they've plotted that against weight percent acetic acid in the water phase. Just as a rough eyeball on this, right? It looks like the slope changes depending, it's concentration dependent a little bit, but if we just kind of eyeball this, you come up to here and you come across over into here, this shows a distribution coefficient that's less than 1.6 for sure. second reference that I found with this system showed this phase diagram, something very similar to this one. They were examining, again, different systems here, but it's acetic acid, water, and then a couple different alcohols shows up. But again, shows the significant miscibility. Both of these papers provide enough information that we could get a couple of tie lines from it, which would allow us to do analysis where we have partial miscibilities, which gets a little more involved, a little more complicated. Looks to me like their distribution coefficients, these are for the various tie lines, so they're basically concentration dependent on here. You have to refer back to it, but it looks like for the acetic acid, its distribution coefficient more around between 1.3 and 1.4 rather than 1.6. So again, the point of all this is that getting the equilibrium data is a tough part on a lot of these problems. Once you know how to do the mass balances, energy balances, using things like Kremser's methods and McCabe-Thiele and all that, it really comes down to the collecting appropriate data, thermodynamic data for these kinds of systems. Perry's Handbook. Here's a section out of Perry's Handbook that they picked and chose. You can see down here acetic acid, 1-butanol. What you don't see is that all these are with water. That's elsewhere it's further up in the table. I just picked out a portion of it. And there's our 26.7, which are temperature here, and there's that 1.613 that they were using for it. I did find one additional reference on this that shows this kind of system again. So if we look, just do kind of a rough estimate here. Here's 10% acetic acid in water. Curve 2, it's this curve here, is for the butanol. So if we look at it, we go up here and we come across, I don't know, it sure doesn't look to me like 1.6. It looks more like 1.3. But I'm not sure. So anyway, we used it because that's what your textbook has and what Perry's had. But again, this is the tough part of some of these problems, is finding good data for this. And sometimes that means at some point somebody's going to have to go out and make measurements, right? Go do some analytic chemistry, to actually figure it out. Titrations, spectroscopy, refractive index, all kinds of ways of measuring concentrations, but that's what it comes down to a lot of times. Okay. Any questions, comments? All right, so what I want to do to kind of wrap this up is to take a look at one of these more concentrated problems. We'll see how much time we have. If it looks like I have enough time to cover what I would like to talk about for chapter 14 on Friday and that following Monday, maybe we'll look at one of these other systems. We'll see how much time we have on Monday to do that. Okay. Other than that, I think we're going to stop here for today, and have a good weekend. All right. See you Monday.